Hello, this is Philip Myers of PEMY Consulting. This is Unit 4, Part B. In this unit and the next two units, we'll talk a little bit about Bernoulli's liquid flow equation. What you see here is a calculus model for an incompressible steady flow. This is called a streamline. This is a trajectory that a particle would take if it were to flow in the moving liquid. This little cylinder has a differential area on the front and another differential area here, and a slight difference in pressure, P, and a different pressure here. Gravity is acting down on this little fluid element. By using calculus, you can determine Bernoulli's equation. We'll do that in a little while. We'll show the Bernoulli's equation. The purpose of this is just to show you how Bernoulli's equation is derived. Before we do that, though, let's talk about dynamic and static pressure. It's often said that static pressure plus dynamic pressure is total pressure. This considers a point in the fluid flow. What this is saying is that the total energy or head or elevation, if you had a tube like this sticking out of a pipe with pressure and a flowing liquid, it would rise up here and here at the same elevation. Now we are neglecting friction. The important point is that if you project this over here, this component is the velocity component or dynamic pressure, and you can see that it increases here. It increases because the velocity in this neck down section of the pipe is higher than the velocity in the larger section of the pipe. So basically the sum of this static pressure, which is this part here, and the dynamic pressure is a constant, regardless of what the velocity is in the pipe. We'll work the units out for the blue symbols, but they will be the same for every other symbol here and here, as we've shown earlier by consistency and homogeneity of units. You should work that out for these other terms. Now I'll start with v squared over 2, and this is the energy form of Bernoulli's equation that was derived directly from the streamline diagram I showed you earlier. Now you might ask, how in the world you get energy out of meters squared per second squared? This is a velocity squared. Well, the trick is that you multiply by 1 using kilograms, and by doing so now I can extract a kilogram meter per second squared. That's a Newton, and I'm left with a meter per kilogram. A Newton meter we know is a joule, and the kilogram is down here. So this is energy per kilogram. That's the energy form of Bernoulli's equation. Now if we multiply by rho, we have the pressure form of Bernoulli's equation. Here we have rho, which is kilograms per cubic meter. We know that velocity from here is this term, and when we simplify units, we end up with newtons per square meter. This is pressure. In this case it's called dynamic pressure because we're talking about the velocity component of pressure. In this last form we have the head form, which is height or length. We can get this by dividing by g. So dividing this equation through by g, we have this. Now the units for gravity are based on W equals mg. If we rearrange that, we end up with newtons per kilogram. So we know that v squared over 2v squared is this component here in terms of units. So this is the v squared, and then we can take the kilogram per newton dividing by this term and ending up with this. You can see that the kilograms will cancel and we'll end up with joules per Newton. That's the same as Newton meter per Newton, and we get another cancellation and we're left with meters. Now I want to look at Bernoulli's equation. P0 is the stagnation pressure. That's the total pressure. It's the pressure where if you brought the liquid velocity to zero, or at the tip of a pitot tube, that would be the stagnation pressure. It's made up of the static pressure, the dynamic pressure, and then the head, the elevation pressure. Let's look at these units. We know that a pressure is newtons per meter squared, pascals, but this is a kilogram meter per second squared, and we have meters squared here, and so this becomes kilogram meter second squared. Mass, length times squared. So we verified one side of the equation. I've just done the pressure side, the first term. You can work out these other terms, but they will cancel out, as you can see, rho v squared, and you get that cancellation, so that is correct. And in the last one, rho g z, you get two of these to cancel out with the 3 there in mass, length times squared. So this is consistent and homogeneous. Now when working with units, it's best to be systematic to avoid mistakes. You always want to keep F equals ma in mind. In SI, you had best know that a Newton is this unit combination. It's easiest just to remember it so you don't have to constantly look it up. And of course you have to know the USCS version of force. Write out all the units, and cancellation is by far the most effective way of reducing errors. You want to know that pound force and pound mass have the same numeric values in the USCS, but they're different units. And it's good to distinguish them with a subscript. By using consistency and homogeneity, you can check your equations for proper manipulation and results. In the next unit, we'll talk more about Bernoulli's flow equation. Thank you.